So we have 4 routers in GNS3. R4 is the ISP. 3 interfaces with IPs, no routing protocol, and no awareness that DMVPN exists. Its sole purpose is to forward packets between subnets and nothing else. R1 is the hub, headquarters. Runs mGRE, access the NHRP server, anchors the EIGRP overlay. R2 and R3 are spokes. They're branch offices. They register with the hub via NHRP and learn routes through EIGRP running over the tunnel. Each site has a loopback 0, reachable for testing. Underlay addressing R1 to R4 on fast Ethernet 00, 10.0.1.0 with a 30-bit subnet mask. R2 to R4 on fast Ethernet 10, 10.0.2.0 with a 30-bit subnet mask. R3 to R4 on fast Ethernet 1.1, 10.0.3.0, 30-bit subnet mask. The overlay is 172.1.6.0.0, 24-bit subnet mask across the DMVPN tunnel. Loopbacks are 192.168.1.0, 24-bit subnet mask, 192.168.2.0, 24-bit subnet mask, and 192.168.3.0, 24-bit subnet mask. Underlay routing is static defaults on each site pointed at R4. R4 doesn't need anything. All 3 networks are directly connected to it. Moving on to the configurations. On R4, we have 3 interfaces with 3 separate IP addresses. That is the extent of the configuration for R4. Moving on to R1, which is the hub router, we're going to take a quick look at the IPSec policy right about here. This initiates Phase 1 negotiation, AES 256 encryption, SHA 256 integrity, Diffie-Hellman group 14, and pre-shared key auth. Now, taking a look at this particular line right here, crypto IPSec key, the wildcard address in this section is intentional. In DMVPN, spokes form IPSec security associations dynamically. When a Phase 3 shortcut triggers between 2 spokes, they need to negotiate encryption on the fly. The hub cannot predict every spoke pairing ahead of time, so the key gets bound to any address. Taking a look at the transform set, this initiates transport mode, not tunnel mode. The mGRE tunnel already handles encapsulation. Adding another IP header on top wastes bytes and creates fragmentation problems that you do not need. Taking a look at the IPSec profile, this profile gets applied to the tunnel interface directly. No crypto maps, no ACLs. So, taking a look at the tunnel on R1. Remember, this is the hub router. Taking a look at tunnel mode GRE multipoint. This is what makes it DMVPN instead of standard point-to-point GRE. The hub accepts connections from any spoke through a single tunnel interface. Now, NHRP map multicast dynamic issued right here. This allows the hub to accept multicast registrations from spokes as they come up. Without this, EIGRP hellos do not cross the tunnel, and you do not achieve any neighbor adjacencies. Taking a look at NHRP redirect, this is the phase 3 command on the hub side. When the hub sees spoke-to-spoke traffic transiting through it, it sends a traffic indication message back to the originating spoke, telling it to resolve the destination directly via NHRP. And tunnel key 100. This has to match across every router in this particular DMVPN cloud. This prevents accidental peering if you're running multiple overlays on the same transport infrastructure. And tunnel protection IPSec profile. This binds IPSec to the tunnel, and it makes everything in and out of this particular tunnel encrypted. Now, taking a look at R2, we're going to take a look at the tunnel, interface tunnel 0, right here, NHRP map. This is a static mapping that tells the spoke where the hub lives on the underlay. The spoke cannot discover this dynamically. It needs at least one fixed point of reference to bootstrap. And in NHRP NHS, this designates the hub as the next hop server. The spoke registers with this address, and it uses this particular address for NHRP resolution. IP NHRP shortcut. This is the phase 3 command on the spoke side. When R2 receives a traffic indication from the hub, it fires an NHRP resolution request directly to the other spoke. And it gets back the MBMA address and installs a shortcut route that overrides the EIGRP learned path through the hub. Make note, this only occurs in the forwarding table and not in the RIB. And IP NHRP map multicast right here. This forwards multicast traffic to the hub's physical address so that EIGRP hellos get there. The configuration on R3 is essentially identical to R2. These are both spoke routers. Okay, now we're moving on to the verifications. We're going to do this from the bottom up. And we are going to start by pinging R1 from R2 and R3, R1 being the hub router. So ping 10.0.1.1 on R2, and we're good. We're going to ping 10.0.1.1 on R3. We are good there. Now we are going to go over to the hub router, and we're going to issue show IP NHRP. And we have both R2 and R3, those being our spoke routers, and show IP NHRP. And next we're going to show DMVPN. And once again, we have both spoke routers and the output of show DMVPN. Now on R1, we are going to check EIGRP. First, we're going to issue show EIGRP neighbors, and spoke 1 and spoke 2 are both there, and we are going to issue show IP route EIGRP. And once again, we have the expected output. Now, we are going to take a look at the IPSec security associations on R1. So we're going to issue show crypto ISACamp SA, and we have the expected output. Both machines are in the QM idle state. And show crypto IPSec SA. And we have the expected output there. Now we're going to take a look at the crypto session with show crypto session detail. And as you can see, both of the spoke routers are paired on the hub router. So we have the expected output. So to demonstrate the formation of the phase 3 shortcut, first we are going to issue show IP NHRP shortcut. And we have nothing there. Then we're going to take a look at show IP route NHRP, and again we have nothing there. So if we issue a trace route on R2 to 192.168.3.1 with a source of 192.168.2.1, let's see that occurs in 2 hops. So our next step is to trigger the NHRP shortcut formation. So ping 192.168.3.1, the source at 192.168.2.1, and we are going to repeat this 100 times. This will generate sustained traffic from R2 to R3. The hub will see this, and then it will fire an NHRP traffic indication back to R2. R2 sends an NHRP resolution request directly to R3, gets R3's NBMA address, and then it installs a shortcut that overrides the EIGRP path. So to verify this, we're going to take a look at show IP NHRP shortcut. And as you can see, we have a route to the loopback on R3. Show IP route NHRP, and again we are showing a route to the loopback on R3. So if we do a trace route to 192.168.3.1 with a source of 192.168.2.1, you'll see this occurs in 1 hop now. This is control plane and data plane separation in action. The hub does the signaling. It tells the spoke where to go to resolve the destination. The spoke builds the shortcut and then forwards the traffic directly. The hub gets out of the forwarding path once the redirect fires. And if we take a look at the crypto session with show crypto session detail, you'll see there's a new IPSec session between R2 and R3. This formed when the shortcut was created. Being able to read show crypto session detail and correlate SAs with tunnel endpoints, I didn't have that when I first ran this in my home lab. I could see the sessions, but I could not connect which SA belonged to which tunnel relationship. Once that correlation clicked, troubleshooting stopped being guesswork. Full configs and the README with the IP addressing table and a troubleshooting guide are on my GitHub. Link in the description.